Welcome to the deep dive. We're zeroing in on something absolutely crucial for the strength of your home, especially if you live where the ground can get a little shaky.
Yeah, that's right.
Today we're talking about the hidden hero in your foundation, steel reinforcement, or rebar. Specifically, how it helps homes in earthquake-prone areas, what the building codes call seismic design categories, D0, D1, and D2.
Right, as laid out in the 2024 International Residential Code.
Exactly.
Think of it like this. We're going beneath the surface, really, to understand the steel skeleton that gives your foundation its resilience. These seemingly small details are actually fundamental.
Fundamental to how well your house will hold up when those powerful seismic forces come into play. And why should this grab your attention? Well, if you're in places like California, Utah, maybe even parts of South Carolina, Alaska, or Hawaii, all areas we'll touch on. Understanding foundation reinforcement is key.
Absolutely. Whether you're thinking of buying, building, or you're just, curious.
Knowing what's happening underground can really give you peace of mind. Earthquakes generate incredible forces, and the foundation is where your home meets that energy head-on.
It's the critical interface.
So we'll be focusing mainly on the 2024 IRC, the International Residential Code, and also pulling some insights from the pros at InterNACHI.
The International Association of Certified Home Inspectors. Good stuff there. So, okay, let's start by cracking open what these seismic design categories D0, D1, and D2 actually mean. What are they telling us?
Well, essentially, these categories, D0 through D2, they're a way of saying, okay, this area has a moderate to high chance of significant earthquake shaking.
It's like a risk assessment baked into the code.
Exactly. It's a heads up that stronger ground movement is expected compared to, say, areas in lower risk categories like A or B.
And because of that higher risk, the building codes step things up. They demand beefier structural elements to help homes withstand those stronger forces.
Right. And it's not just the stereotypical West Coast. People often just think California.
That's a common misconception. Well, yeah, much of California, along the San Andreas Fault, and the western edges of Oregon and Washington near the Cascadia subduction zone are definitely included.
Sure.
These categories also pop up in the Intermountain West. Think parts of Utah near the Wasatch Fault, even the New Madrid seismic zone.
Right, affecting sections of Missouri, Arkansas, Tennessee, Kentucky, Illinois.
Yep. And don't forget Charleston, South Carolina, with its own seismic history, plus significant parts of southern Alaska and the Big Island of Hawaii.
It's definitely a much wider spread than many people might realize, but it's also crucial to understand pinpointing the exact category for your specific address isn't just looking at a broad map.
No, it's more granular than that.
Yeah.
It involves factors like the specific type of soil under the property.
Which can make a big difference.
A huge difference. Also, how close you are to known earthquake faults, the history of seismic activity locally, and something engineers call anticipated ground acceleration.
Okay. So where do you find that specific info?
Your local building department is really the go-to source. They have those detailed seismic zone maps that incorporate all these local factors.
Good to know. Okay, so now we have a sense of where these higher risk areas are. Let's talk about why the foundation design itself is so critical for standing up to earthquakes. What's the basic job it's doing?
Well, picture the whole building shaking violently side to side. All that lateral energy, all that sideways force, it all gets channeled down into the foundation. The entire house is essentially trying to slide right off its base.
So the foundation's main job is to resist that, to grip the earth.
Exactly, to grip the earth and resist that sliding motion. And, the InterNACHI material points out two main ways it does this. Width and depth.
Width and depth, okay.
Yeah, the wider the foundation footing, the more surface area is in contact with the soil. More contact means more friction resisting that slide.
Makes sense, like trying to push something wide versus something narrow.
Precisely. And then there's depth. The deeper the foundation extends into the ground, the more the surrounding soil physically pushes back against it. That's what engineers call passive soil pressure.
Oh, okay. So the earth itself helps hold it in place.
Right. More contact, horizontally or vertically, means more stability. It's interesting, too, the material mentions how slab-on-grade foundations often show pretty good earthquake resistance.
Because they have that huge footprint, that large frictional surface.
Exactly that. That broad base provides a lot of friction, which brings us right to the main event here, rebar. We've talked about the forces, but how does this steel reinforcement embedded in the concrete actually help?
Okay, yeah, let's break that down. Concrete, as we know, is incredibly strong when you squeeze it. Compressive strength is its superpower.
Like holding up a heavy column, no problem.
But its tensile strength, its ability to resist being stretched or bent, that's its weak spot. It's relatively brittle in tension.
And what happens during an earthquake? You get all sorts of pulling and bending forces acting on that foundation. It's not just compression anymore.
Right. Things like maybe concentrated weight from a big fireplace or uneven settling of the soil, leaving parts of the foundation kind of hanging.
Or just the pure sideways and even upward tugging forces from the seismic waves themselves. All of these create stresses trying to pull that concrete apart.
Exactly. So rebar steps in. It's the reinforcement. It's like those steel bones we mentioned earlier, embedded right inside the concrete.
Providing the missing piece, the tensile strength.
Yes. It helps prevent the concrete from cracking and eventually failing under those pulling and bending stresses. Without it, the concrete might look solid, but it could just buckle or fracture.
And we typically see certain sizes in residential work, right?
Yeah, usually hashtag 4 rebar, which is about ½ inch in diameter, and sometimes hashtag 5, which is around 5/8 of an inch thick.
And this reliance on rebar and also anchor bolts, which we'll get to, is a big step up from older building practices.
You mean like those concrete keyways?
Yeah, those little interlocking grooves they used to put between the footing and the wall. It was an attempt to stop sideways movement, but modern codes really emphasize the integrated strength you get from rebar and proper anchoring. It's a much more robust system.
Okay, so it creates a stronger, more unified foundation.
Yeah.
How specifically does this reinforcement counteract those main earthquake forces, the sideways push, the uplift, the shearing, and prevent those really scary failures?
Well, think about what happens without enough rebar. Those lateral sideways forces can easily cause horizontal cracks in the foundation stem walls. That's shear cracking.
Right, I've seen pictures of that.
Yeah. And if the vertical rebar isn't spaced closely enough, or isn't there, the walls can actually split vertically under the stress.
Ouch.
Uplift forces can literally pick sections of the foundation right off the ground. And ultimately, the worst case is the whole house just shifting clean off its foundation if it's not tied down properly.
Sounds like a complete disaster. So the rebar prevents that by...
It creates a connected network, a steel framework within the concrete. This allows the whole foundation system to flex and move slightly, to absorb and redistribute the earthquake's energy without just shattering or collapsing.
So it's not about being totally rigid, but having toughness.
Exactly. It's about ductility, the ability to deform a bit without breaking. That internal steel framework provides that.
Okay, let's get into the nuts and bolts then. What are some of the main rebar requirements in these specific zones, D0, D1, and D2, according to the 2024 IRC? Let's start with maybe the most common type, concrete stem walls on separate concrete footings.
Okay, for that standard setup, the IRC section R403.1.3.1 mandates vertical reinforcing bars. They have to be at least 4 size.
The ½ inch ones.
Right. And placed no more than 4 feet apart along the wall. And here's a really critical detail. These vertical bars need to have standard hooks bent at the bottom.
Your hooks?
Yeah, like a 90-degree bend that reaches all the way down near the bottom of the footing. And then the top end has to extend up into the stem wall at least 14 inches.
Ah, so it's physically locking the wall and footing together.
Precisely. It anchors the wall securely to the footing. That connection is vital.
Okay. What about horizontal steel in that type of foundation?
Good question. There also needs to be horizontal rebar, at least 1 4-bar, placed within the top 12 inches of the stem wall.
Near the top.
Yes. And another 4-bar located about 3 to 4 inches up from the bottom of the footing itself.
Okay, so top and bottom horizontal bars too.
Right. This horizontal steel helps tie the vertical bars together and resist cracking that might run along the length of the walls. It distributes the stress.
Got it. Now what about monolithic slabs, the ones with turned-down footings, where the slab and the footings are all poured at once?
Right, the single pour. For those, IRC section R403.1.3.2 gives a couple of options. You can either put 1 4-bar near the top and 1 4-bar near the bottom of that thickened edge, that turned down footing part.
Top and bottom again.
Or the alternative is you could use 1 slightly thicker 5-bar or 2 bars placed right in the middle third of the footing's depth.
Interesting. So a couple of ways to achieve that reinforcement in a monolithic pour. What if the slab and footing aren't poured together? If it's non-monolithic?
Ah, yes. If you have, say, a footing poured first and then a stem wall or slab poured on top later, that's non-monolithic construction.
Yeah.
In those cases, IRC section R403.1.3.3 requires vertical dowels.
Dowels, like short pieces of rebar.
Exactly. Short vertical rebar pieces installed at that construction joint where the 2 concrete sections meet. They stick out of the first pour and get embedded into the second pour.
We'll tie them together.
Absolutely. It prevents one part from shifting relative to the other during an earthquake. Think of it like stitching the two pieces together with steel. It's a really important connection.
Makes total sense. You need that continuity. What about inside the house? Any special rules for interior footings under load-bearing walls?
Yes, in these higher seismic zones. If you have interior footings that support load-bearing walls or those braced wall panels we rely on for earthquake resistance, and if they're poured monolithically with the slab, IRC says they need to extend at least 12 inches down from the top surface of the slab.
So they need sufficient depth, even if they're inside.
Right. Ensures they have enough mass and embedment to properly support those critical structural elements above them.
And, it's not just about having the right size rebar spaced correctly. How it's actually placed in the concrete matters too, doesn't it?
Oh, absolutely critical. The code covers this in R403.1.3.5. In stem walls, for example, those vertical bars should be centered within the wall's thickness, not too close to either face.
Okay.
And all the reinforcement needs to be held firmly in position while the concrete is being poured. You use things like wire ties or plastic chairs to keep it from shifting.
So it ends up exactly where it's supposed to be.
Yes. And finally, there has to be enough concrete surrounding the steel on all sides.
Why is that important?
Two main reasons. One, it protects the steel from moisture and corrosion, basically rust. Two, you need enough concrete around the bar for the bond between the steel and concrete to develop properly. That bond is how the stress gets transferred.
Right, so placement and cover are just as important as the bar itself. Now, are there any exceptions? Situations where you might not see this level of reinforcement, even in D0, D1, or D2 zones?
There's one main exception. It applies to detached 1- and 2-family homes, 3 stories or less, that have stud-bearing walls, typical wood framing.
Okay.
In those specific cases, isolated concrete footings, like the ones you might put under a single deck post or an interior column that isn't part of a braced wall line. Those simple footings are allowed without all the vertical and horizontal rebar we just discussed.
Why the exception there?
Because those isolated posts or columns typically aren't carrying the primary earthquake resistance loads for the building. The sideways forces are mainly handled by the braced wall panels, which do need the heavily reinforced foundation beneath them.
Ah, okay, so it depends on what the footing is supporting. But rebar isn't the only piece of the puzzle connecting the house to the ground, right? What about anchor bolts and those metal straps you sometimes see?
You're absolutely spot on. Rebar makes the concrete itself strong and tough, but you still need to firmly attach the wooden house frame to that concrete. That's where anchor bolts come in, IRC R43.1.6.
Okay, what are the key things there?
They need to be embedded at least 7 inches deep into the concrete. Spacing is usually no more than 6 feet apart along the sill plate, but that can be reduced closer spacing in higher seismic areas or near wall ends.
And they need those big washers, right?
Yes, critically important. Those 3-inch by 3-inch square plate washers are required in these seismic zones. They help spread the pulling force from the bolt over a larger area of the wood sill plate, preventing the bolt head or nut from just pulling through the wood during shaking.
Makes sense.
And one more detail. The bolts shouldn't be installed too close to the edge of that wood sill plate.
Got it. And the straps and tie downs, where do they fit in?
These are especially crucial in houses with stem wall foundations, often connecting different levels of framing or tying wall studs directly down to the foundation. They act like continuous metal connectors.
Holding everything together vertically.
Exactly. They provide uplift resistance. You'll often see them specified at corners, around large openings like garage doors, and at the ends of braced wall panels. And they have specific load ratings they need to meet. They work with the anchor bolts to create a complete load path, resisting those forces trying to lift or slide the house.
Wow, there's a lot going on there structurally. But, a lot of this, the rebar, the embedment depth of the bolts, it's all hidden once the concrete is poured and the walls are up.
That's the challenge, yeah.
So as a homeowner, maybe not a pro inspector, what are some clues you could look for? Anything that might suggest whether these things were done right or maybe not?
That's a smart question. It's tough because you're right, the most critical stuff is hidden. But you might see exposed ends of rebar in an unfinished basement or crawl space, maybe where a future addition was planned. If you happen to have the building plans, they should show the reinforcement schedule.
Okay.
You can look closely at construction joints where new concrete meets old. Were dowels used if needed? Are there big offsets? Also, look for signs of movement. Significant cracks, especially diagonal ones in the foundation walls, or any separation between the foundation and the house framing.
So visible distress signals.
Right. You can also visually check for the presence of anchor bolts along the sill plate in the crawl space or basement. Are they there? Do they have the big square washers? Are the metal hold-down strats installed where they should be, especially at corners or near large openings?
Okay, so checking the visible connections.
Yeah. Just generally observing how well the house seems seated on its foundation can sometimes offer clues. But again, you have to remember the really crucial rebar within the concrete is invisible without specialized tools or destructive testing.
Understood. What about older homes? You mentioned earlier building practices were different. Many homes were built before these stricter seismic codes came into effect.
Absolutely. Homes built before, say, the mid-1970s, especially in many parts of the U.S., are very likely to lack the amount of foundation reinforcement and connection details we've been discussing. The codes just weren't as stringent then regarding seismic resistance.
So if you have an older home in an earthquake zone, what should you look for?
Look for signs of retrofitting. Maybe newer-looking anchor bolts have been added. Sometimes they use expansion bolts drilled into the existing concrete, or bolts set with strong epoxy adhesive. You might see added plywood sheathing or metal bracing on the cripple walls and the crawl space.
Okay, strengthening those short walls.
Exactly. Sometimes you might even see evidence where steel dowels were drilled and epoxied into the existing foundation to better connect it to a newer wall or slab section. And of course, any documentation of recent foundation repairs could indicate either past damage or hopefully a proactive upgrade.
Right. It's also not just about the concrete and steel itself, is it? The ground around the foundation matters too. Drainage and soil type.
Hugely important. Poor drainage around the foundation, as covered in IRCR 405, is a major enemy. If water pools against the foundation, it saturates the soil, reducing its strength and stability. Over time, it can weaken the concrete itself.
It makes it more vulnerable during an earthquake.
Definitely. Look for those telltale signs. Water stains on foundation walls, that white powdery stuff called efflorescence, dampness, or puddles in the crawl space or basement. Also, check the grading. Does the ground slope away from the house like it should, or does it funnel water towards it?
Those are definite red flags. And the soil type itself, does that play a big role?
Yes. The code and resources like InterNACHI highlight this too. Different soils behave differently during shaking. Loose, sandy soils, for example, can actually amplify the ground motion. It's like shaking a bowl of Jell-O versus a solid block.
Okay, that makes sense.
Expansive clay soils, the kind that shrink dramatically when dry and swell up when wet, can cause differential settlement. Parts of the foundation move up or down relative to others, putting stress on it before an earthquake even happens.
Setting it up for failure.
Potentially, yeah. And then you have liquefiable soils, usually loose, saturated sands or silts, which can temporarily lose all their strength during strong shaking and basically behave like a liquid. Houses can literally sink or tilt. Those require very specialized foundation designs.
Wow. How do you find out what kind of soil you have?
It's a good idea to investigate. The USDA's Soil Survey website is a great starting point for general soil types in an area. Your local building department might also have geotechnical reports on file, especially for newer subdivisions or areas with known soil issues.
Okay, worth looking into. So if someone has an older home, or maybe they know they have tricky soil or poor drainage, are there practical steps, retrofits they can take to make their home safer?
Yes, definitely. There are several common seismic retrofits that homeowners can consider. FEMA has excellent resources on this, like publication P530.
Okay, like what?
Well, one of the most cost-effective is foundation bolting. If the house isn't bolted or the existing bolts are inadequate, adding proper anchor bolts is a huge step.
Connecting the house to the concrete?
Exactly. Then there's cripple wall bracing. If you have that crawl space with short stud walls between the foundation and the first floor, reinforcing those walls with plywood or oriented strand board, OSB, is critical to prevent collapse.
Right, strengthening that weak link.
You can also add shear walls, basically reinforcing existing walls with structural panels to resist those sideways racking forces. And sometimes adding metal straps, like hold-downs, can improve the connection from the walls down to the foundation.
Is this kind of work incredibly expensive?
It varies a lot depending on the house size, condition, and what exactly needs doing. But a general range might be somewhere between, say, $3,000 and $7,000 for bolting and cripple wall bracing, which, when you think about the potential cost of earthquake damage,
It seems like a pretty reasonable investment, kind of like an insurance policy.
that's a great way to put it, a very valuable insurance policy.
To really drive home why all this matters, let's maybe look at a real-world example. The 1994 Northridge earthquake in California seems like a key moment.
Oh, absolutely. Northridge was a magnitude 6.7 quake, and it really brutally highlighted the difference foundation design makes. Homes that lacked proper reinforcement, especially older ones.
What happened to them?
Many experienced catastrophic failures. We saw complete collapses, houses shifting dramatically off their foundations, cripple walls giving way, just devastating damage.
But what about homes built to newer codes with the reinforcement?
Those generally fared much, much better. They might have had some cosmetic damage, maybe some cracking, but the structure often remained largely intact. They were repairable, not total losses.
And the financial difference must have been huge.
Enormous. The sources mention the cost difference between repairing a properly reinforced home versus having to completely replace an unreinforced one often exceeded $200,000 back then. Imagine that today.
Wow. And Northridge wasn't just a tragedy, it actually spurred changes in building codes, didn't it?
Yes, it was a major catalyst. The lessons learned directly led to significant strengthening of seismic provisions in the building codes that followed, like the 1997 Uniform Building Code, and then carried into the International Residential Code we use today. Sections R403.1.3 through R403.1.6, dealing with foundation anchorage and reinforcement in seismic zones, were heavily influenced by what engineers observed after Northridge.
So the codes got tougher because of it.
They did. And there's a compelling statistic mentioned in the InterNACHI material. In one specific neighborhood studied after Northridge, where soil conditions were similar, homes that had properly reinforced foundations experienced about 60% less structural damage compared to nearby homes without that reinforcement.
60% less damage. That's incredibly significant.
It really demonstrates the effectiveness of these code requirements in a real-world event.
So pulling this all together for homeowners listening, especially those in these moderate to high seismic zones, what's the main takeaway?
I think it's about appreciating that the foundation work, the rebar, the bolts, the connections, it isn't just some optional upgrade or a minor construction detail. It's truly a fundamental safety system for your home.
Right. It's core to its survival in a quake.
Exactly. And that highlights why things like thorough inspections during construction are so valuable. It also means understanding the potential vulnerabilities if you live in an older home and making informed choices about maybe doing some retrofitting.
And if you're buying a home.
Definitely factor in the seismic risk of the location. Ask questions about the foundation. Was it built to modern codes? Has it been retrofitted? Hiring your own qualified home inspector, especially one familiar with seismic issues, is crucial. Taking the time to get educated is really empowering.
Absolutely. So it seems crystal clear. Properly reinforced foundations are this critical, often invisible shield against earthquake damage. It's not just about preventing some cracks. It really can be the difference between keeping your family safe and facing devastating loss when the ground decides to shake.
Well said. And it leads to, I think, a really important final thought for you, our listener. Thinking about these specific earthquake risks where you live or maybe where you're considering moving. What are the most crucial questions you should be asking when you evaluate a home's foundation? Whether it's an existing house or one under construction, try to think beyond just the surface appearance.
That's a great point to ponder. What lies beneath? If you do want to dig deeper, we definitely recommend researching your local seismic building codes. They can vary. Explore the resources on earthquake safety from FEMA, especially publications like P530 for retrofitting and P232. And maybe even look into those local geotechnical or soil reports we mentioned.
Yeah, understanding these details really is a key part of ensuring your home's overall safety and its resilience for the long haul.
Couldn't agree more. Thanks for taking this deep dive with us today.